Welcome to the voices of transparency and excellence. We're not pivoting, the world is spinning, like a top. Let's stop, figure things out, get some answers. Come with us on this ride. Warm regards, Rick and Judy.
Welcome to our podcast series where we address crucial topics impacting our campus and community. I'm Judy Brown Clark.
And I'm Rick Gatteau, and today we're going to be talking about the moon and how a Stony Brook professor has been chosen by NASA to be on Artemis' first lunar surface science team for the planned 2028 mission of going to the moon. We are so pleased to have Timothy Glotch with us. He's a professor and chair of the Department of Geosciences here at Stony Brook University. Tim, thanks so much for being on today's episode.
Thank you for having me. This is exciting.
We know you're a celebrity now, so we're glad you fit in some time to talk with us. Judy and I were just talking before we went on air, just obviously about all the amazing things you've been able to showcase in terms of your experience. But let's talk about Artemis II. So the astronauts became the first humans to observe the far side of the moon and an Earthrise with the naked eye since the Apollo 17 mission back in 1972. And as I'm sharing with you what you already know, the Artemis II mission topped the record for how far humans have traveled, a whopping 252,756 miles from Earth. And we know the Artemis II crew also included the first woman and the first black astronaut, as well as the first Canadian to go on a mission around the moon. So can you share with us a little about your experience observing this, speaking about it, and tell us more about the call that you got to be asked to be part of that 10-person team to help plan future Artemis missions?
Yeah, sure. Happy to talk about all that. Yeah, so as you mentioned, the Artemis II mission flew around the far side of the moon, came back to Earth, safely landed in the Pacific Ocean. It was a crucial test of the Orion spacecraft, which is the capsule that the astronauts live in while they're on their trip to and from the moon. Artemis I was an uncrewed version of that, so it's just a basically empty spacecraft. But this was testing crucial life support technology. It was testing the astronauts' ability to work and operate in space over this long duration mission. And after some issues with the Artemis I reentry, it was also testing a new reentry trajectory to kind of take some pressure off the heat shield on its way back to Earth. And it was a resounding much of the country, I was cheering along and I was just wrapped, with attention. And it was inspiring to see this. It was inspiring to look at the crew and how they were interacting with each other and just the awe that they had. And it was coming through loud and clear, even though that they were hundreds of thousands of miles away, right? And then you mentioned the Earthrise picture that they took, that Reed Wiseman, the commander of the team, the crew, got as they were coming around the far side. I mean, I think that's a instantly iconic image. I said, when I was doing another show, I think that is instantly going to be used on social media. It's going to be in textbooks. It's going to be used, and we're going to be seeing this 40, 50 years from now. That's how, crucial and how important that image is. So Artemis II, huge success. As you mentioned, I was selected to join the Artemis surface science team. So that right now is planned to be Artemis IV. Artemis III is going to be a mission that is going to be in low Earth orbit, and it's going to test some other technologies. But Artemis IV, we're going to land a crew of 4 astronauts on the surface of the moon at the South Pole. About a week before the Artemis I launch, I got a call from NASA that a proposal I had written to join the Artemis geology team was selected, one of 10 new scientists being added to the team. Actually, as soon as I'm done with this podcast, I'm going on a Zoom call for our weekly Artemis surface science team meeting. So we're already getting to work. And over the next 2 years, we're going to be working on analyzing potential landing sites. We're going to be planning potential EVAs. Those are extravehicular activities that the crew will do when they land on the surface. We're going to be eventually, when the crew is selected, hopefully working with them and the people who train them to do geology so that they can select the best samples to bring back to Earth for us to analyze in our labs. We're still doing amazing science with Apollo samples that were returned more than 50 years ago. So these samples that the Artemis astronauts are going to bring back are going to teach us so much more about the moon because they're selected from a completely different area of the moon. And it's super exciting. And we've just gotten started and I can't wait to dive in more.
So this is really exciting. So can you tell us a little bit more about your role or some of your strategic thinking? And so you talked about being on the surface science team, and it's fascinating to think about what would go into exactly where the landing site would be, what samples to bring back, what kind of training that the mission team would need, and so on. So when you think about that, how will you help them locate, or what are some of the decision making of landing site, knowing what samples to collect so that you can, you've got finite time.
Yep.
And so how do you utilize that time to the highest?
Yeah, so it's kind of a divide and conquer strategy. There are lots of folks on this team, both within NASA and at other universities and research institutions, just like me here at Stony Brook. So there are lots of potential landing sites. There's not one that hasn't been chosen yet. We have lots of data from orbiters. So I'm also a co-investigator on a scientific instrument on the Lunar Reconnaissance Orbiter, which has been at the moon since 2009. And it has a super high resolution camera on it that takes pictures at about 50 centimeters per pixel. That's like a 1.5 feet, per pixel. So really high resolution imagery. We have compositional data from infrared spectrometers. And so we can analyze all that data, try to find the best places to land. And so of paramount importance is crew safety. So we have to find areas that are relatively flat. The south pole of region of the moon is actually very heavily cratered. It's very rough in terms of its topography. So the amount of area that's available to land on is relatively limited. And then the lighting conditions at the South Pole are also really weird. So it'd be like trying to do field work in Antarctica at night, right? Because you're right at the pole. The sun is very low on the horizon. So small topographic features cast very long and large shadows. And on the moon, because there's no atmosphere, the shadows are as black can get. It's not like there's, you can see like still see a little bit like you can here on Earth. The shadows are basically as dark as you can get. And so we have to worry about, well, what time of year do we land? What's the season on the moon? Where are the shadows going to be? And we have models that tell us what those are going to be in the time frame. So we have to take all of that into account. We want to be in sunlight where we can collect solar power and where the astronauts can operate. So all of that goes into the consideration of the landing spot. And then, science is something that, we're on the team to help optimize. And so compositionally, we're looking at what areas are representative of the average composition of the lunar crust there. Are there any anomalies that would be interesting to go look at that might represent something different? And then the astronauts will be taught by the geology training team how to identify different types of rocks, which ones they're most likely to see, what other things look like that might also be interesting for them to get. And then they can also use the experience of the Apollo crew, which has been recorded for posterity, to help them understand how they might make decisions on the fly.
Tim, thinking about Artemis II when that mission was happening, my sense is it brought our country together and kind of unified us around this notion of exploring the universe. And I got a sense that just even in K-12 education and colleges, there was this just growing excitement. And it brought a question to my mind of why has it taken so long to get us back to the moon, Fuse? I'm just wondering, tell us why it took so long.
Yeah, no, that's a totally fair question. And for the record, I agree with you. I mean, I think it was incredibly inspiring, and just the amount of people that I heard from who the moon isn't part of their daily life, like it is.
They look at it, but
yeah, exactly.
Exactly.
It was really cool to hear just from friends and neighbors, how excited they were about it. So during the Apollo era, there was a huge political motivation to go to the moon, it was a real space race with the Soviet Union. And records show that President Kennedy wasn't all that interested in the science of the moon. He just wanted to beat the Soviets, and any science that we got was kind of ancillary there. At that time, in the 60s, NASA had about 5% of the total U.S. federal budget, which is a staggering amount. By the early 70s, 1972, Apollo 17, there was a sense of we've been there, we've done that. There were actually further planned Apollo missions, Apollo 18, 19, and 20, that were canceled because it became hard for the government to justify. the cost. And human exploration is more expensive than robotic exploration in general. So there was a pivot back to low Earth orbit with Skylab and then the shuttle program and then the space station. And we were there for, a few decades, right? And then with the strategy of using robots to explore other areas of the solar system. And we've had tremendous successes with robotic exploration. I've been involved in some of those, which has been amazing. But looking to the present day, we really kind of got the sense that, and this started maybe 8 or 10 years ago, that human exploration, yes, it's inspiring, but we can also do a lot more with humans than we can do with robots. Humans can think on their feet. They can identify very easily those anomalies without having to necessarily talk to a crew back on Earth with a long time delay. They have the ingenuity and the decision-making that humans have that right now robots don't. So it took a long time because we're working on a much smaller budget. NASA's total budget is now about 0.5% of the total U.S. federal budget. So as a percentage, it's about 10 times less of the federal budget. So we're doing more with less. And that still, includes all the robotic exploration we're doing, the still paying for the space station. Yeah, it's taken a long time, but we're doing it now. And I think we're doing it with a culture of safety for the crew that was probably not as well developed in the Apollo era when it was like rush, 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 rush. So even though Artemis has been marked so far by some delays and, launch date slips, that has always been done because the safety of the crew has been paramount. And we want to make sure that when we send our colleagues and friends to the moon, that we get them back to Earth safely.
Can you talk more about the heat shield and the concerns about that and what is done to actually ensure safety of any astronaut?
Sure. So the Artemis I spacecraft, when it re-entered Earth's atmosphere, that was the uncrewed spacecraft. After it was recovered, they noticed a lot of pitting and ablation of that heat shield. There was a study done over a period of roughly 2 years to understand what happened. It was more than expected. The study confirmed that if astronauts were on there, they would have survived, but it was a little too close for comfort, I would say. So there wasn't enough time for Artemis II to change the heat shield configuration. For future Artemis missions, they will change the material or the configuration of those heat shields. So what they did after a lot of study and some modeling, instead of changing the heat shield configuration for Artemis II, they changed the reentry trajectory. And basically what they did is they made the reentry trajectory steeper so that the astronauts themselves are feeling more G's on their way in, but the heat shield was under a maximum heating load for a much shorter period of time, almost roughly half the amount of time it was for Artemis I. And the thought was that would reduce the amount of ablation of the heat shield. And so we haven't heard yet what that heat shield for Artemis II looks like. But of course, the Artemis astronauts made it home safely, which was the main point.
So let's talk about the impact on the history of the moon. And it's interesting, you just kind of put it within the framing of what are some of our federal budgets that are allowing this kind of exploration and in these missions. So storytelling will be very important. And so if we think about the location of these shallow ice deposits, which probably is directly why we're going into one of the most inhospitable parts of the moon, which is the South Pole. And coincidentally, I used to sit on as an external advisory committee for the CODEX, the oldest exploration of ice.
Cool.
And the cool thing about that is that they would drill these ice cores, and within those cores, they called it dust, but these particles could give you kind of this really time series of the history of Earth. And I would assume the same kind of knowledge and technology will be used at that same, for Artemis IV. So what are some of the questions that you're looking at asking and answering? Or the second part of that is like, what will we leave behind on the moon that gives us kind of a continuous feed of information?
Both great questions. So you're exactly right that the reason we're going to the South Pole of the moon is because orbital missions have remotely detected ice in these craters at the South Pole that are permanently shadowed. So we call them PSRs, permanently shadowed regions. They haven't seen light for 4 billion years or more. And they're the coldest areas that we've ever measured in the solar system, just a few degrees above absolute zero that we've directly measure those temperatures. So because they're so cold, they essentially become traps for any molecule that's really volatile, like water and other things too. And so over time, over eons, we think that layers of water have kind of been built up and then probably buried by regolith or soil from impacts that have kind of, buried them. But if not with Artemis IV, then with future Artemis missions, we will be exploring those PSRs, trying to sample the ice that's there. And we can do different types of chemical analyses on that ice to tell us about where it came from. Was it deposited by comets that came in from the outer solar system that brought water with them and impacted into the moon? Was it deposited as a result of the interaction of the solar wind, which is a stream of particles that the sun emits that's mostly hydrogen? And those hydrogens can interact with oxygens, kind of like just hanging out on the lunar surface, and hydrogen plus oxygen, H2O is water, and then they can kind of bounce around and then end up in the South Pole in these cold traps. And so we can figure out what the origin of the water is, I think, relatively quickly by looking at the isotopes of oxygen specifically that are in that water. And then depending on how shallow or how deeply it's buried, we can learn about the lunar water cycle, about how water moves around the moon and ends up there. And then we can figure out the timescales over which that has occurred. And more broadly, when we collect samples of the moon, the South Polar landing site is at the very edge of the largest impact basin in the solar system called the South Pole Aitken Basin. This is the largest impact crater essentially in the solar system. And it's kind of the feature on the moon that we use to pin down all of lunar chronology. So if we look at an area on the surface of the moon, we try to figure out how old it is because we need to know that chronology to understand the history of the moon. Geologists use rocks and craters like historians use texts to think about history. Understanding the age of that kind of pins down the chronology of the rest of the moon. So if we can collect rocks from that we think are directly related to that impact crater, and we can bring them back to Earth and figure out how old they are using radiometric dating techniques. Then we actually do some of those types of studies in our building, Earth and Space Sciences building here at Stony Brook. Then we can basically have an absolute knowledge of the chronology of basically every event after that on the moon that has occurred. So that's really, really exciting for us. And you mentioned the kind of the infrastructure that will build up eventually at the moon. So there is a plan for a South Pole base. This part of this is going to come from equipment that's been repurposed. There was originally going to be a small space station around the moon called the Lunar Gateway. This was part of the previous architecture. Kind of as the plans for Artemis have evolved, that didn't really make sense anymore. And so some of the modules that are being built for that, especially by our European partners, are now being thought of as the key components of what will eventually become a Artemis base camp or a lunar moon base. And so having a sustained base at the surface will increase the amount of science that we can do. It'll be built up gradually over time, but you can kind of think of it as a mini McMurdo station that we have on Antarctica, right? It's, there's a season where in Antarctica during the Northern Hemisphere winter where there's lots of scientists down there, but it's crewed year round, even in the harshest winter down in the South Pole. And that really maximizes the amount of science that everybody else can do. So I'm kind of thinking, and I think that's the model that a lot of us are thinking about for a lunar base camp, which is permanently crewed or almost permanently crewed infrastructure that enables more and more science to be done over longer periods of time. So we're not just redoing Apollo where we go to the surface a few times, we plant a flag, we get to make a few boot prints, bring back some rocks, and then we wait for another 50 years. And so to me, this is a really encouraging sign that this base is in the plans, that we're there for an extended period of time to really maximize the science.
Awesome.
Tim, are there other areas, just of your research background, that are able to contribute to the work that you're going to be doing over the next 2 years?
Yeah.
What has prepared you for this moment?
So there's a few things. I think you'd have to ask the review panel who reviewed my proposal, what they think. But I was trying to pitch a few things. One is that my initial expertise and training is in remote sensing, basically using satellite data to help us understand what's on the surfaces of other planets, whether it's Mars or the moon or even Earth and asteroids. And so looking at using remote sensing data to analyze potential landing sites, I think is going to be a big part of my efforts over the next 2 years. I have a lot of experience working with large, complex teams, and I think that's something that's actually super important for something like this. The proposal that I had to write to join the team was very different than anything I've ever written before. They were very clearly looking for someone who works with teams, knows how to lead as well as follow. And I wasn't asked to write a specific science investigation, which I do for almost all my proposals. I had to kind of pitch myself as someone who would be useful to the team, but for lack of a better word, also not be an asshole, And so I think they were really thinking about team dynamics, and it's going to be high pressure, high intensity situations, especially when we're on the surface with a crew and the decision has to be made. And how do we make that decision as a team together? And so I've had some experience leading some larger NASA center teams, and I think that helped. And on thinking about post-mission, we're going to have these samples back, and a lot of the work I do now is analyzing samples in my lab. So I could also pitch myself as someone who will get to help maximize the science of the samples once the samples get back. And that's something that I'm also very, very excited about, is thinking about after the crew returns safely with maybe 30 or 40 kilograms of rocks, getting my hands on some of those rocks and bringing them to Stony Brook.
I mean, it's so interesting that the proposal you submitted, right? You have the scientific knowledge, but it sounded like so much was around interpersonal and team building dynamics are really important. So it's just good to think about where at Stony Brook and the work we do with our students that the content matters, but also the other skills that are maybe what we call the softer skills are equally important.
Absolutely. And it's something I try to do with my own research group, where I have postdoctoral researchers and who are more senior level. They've got their PhDs and they come here to work on research projects. Graduate students and undergraduates all in my lab, as well as a few research professors who I collaborate with very closely. And we try to set up a culture of kind of successive mentorship, where we can have the research professors and the postdocs work and help mentor the graduate students, and the graduate students actually help mentor undergraduate students in the lab. So it's not just me as this kind of one person kind of on top of the research group, telling everybody what to do, but it's a much more of a collaborative team environment. At least I like to think it is. And, even every week we have, Thursday mornings, we have our group meetings and we sit around a table and everybody kind of talks about what they did in the last week. And it's a great place for people to figure out, I have this problem I encountered this week, but somebody else knows how to solve that problem because they encountered it, last year. And that's another way we can kind of build up, teamwork and a sense of belonging and a fellowship, for lack of a better word, where everybody feels like they're in it together, even if they're working on different projects. And there's a sense of collaboration rather than competitiveness.
I think, where we're answering these wicked problems, and I think you've redefined moonshot now, but these are complex questions through conditions.
Yep.
Interdisciplinary, multidisciplinary, transdisciplinary, multi-institutional, and now astropolitical. Yeah. Because as a nation, there's no way, you just talked about it from a financial perspective, but you also talked about how do you leverage different levels of critical thinking, skill building. Some things, your team may be ahead of, others out. So there's no way we can really get a clear understanding of the moon unless we're doing it in a geopolitical way.
Sure.
So what does that look, as you're thinking about this, a sample collection, like who owns that? What does that look like?
Those are great questions. I will say, just thinking about kind of domestically in the U.S., one of the great things about NASA is that it's always been, one of the agencies in the federal government that has had the strongest bipartisan support. Yeah. There are NASA labs in red states, Johnson Space Center. There's NASA labs in blue states, like Goddard Space Flight Center and Ames in California. And it's always had really, really strong bipartisan support, both from a human exploration standpoint as well as NASA science. So that's been really gratifying, and that hasn't changed, regardless of administration. The thinking about ownership of the samples, the analogy or the precedent is Apollo. And so the U.S., collected the Apollo samples. They are owned by the federal government. They cannot be given out to people. I have some in my lab that are stored in a safe under a specific loan agreement with the federal government. So when they are sent to me, I do not become the owner of those samples. I'm a custodian of the samples essentially, and then I have to send them back. And they can be loaned at the discretion of the curator to researchers, throughout. China has recently returned samples robotically from the moon, and with a couple missions, those are owned by the Chinese government. And much like the Apollo samples for us are national treasures, as part of the, as the United States government, the Chang'e samples are national treasures for China. China is working on its own crewed missions to the moon. India is as well on a longer time frame. The U.S. Has led a group of nations through a program called the Artemis Accords, which are basically a group of nations that have signed on to basically the U.S. plan, and that could eventually include sharing of samples and maybe even crew from their astronauts from their countries joining Artemis missions. China's leading another block of countries on an international lunar base plan, including Russia, Pakistan, I think a few other countries. And so there are kind of geopolitical divisions that are forming and have formed. A lot of that is above my pay grade, way above my pay grade. And I find it's best for me to be aware of what's going on, but concentrate on what I'm good at, which is the science.
And one thing I just wonder, there's certain things that are galvanizing as a human race.
Yeah.
Sport, culture, music, art. Do you think it has the potential to galvanize us, at least that understanding of who we are within this universe?
Sure, absolutely. And this goes to, human exploration and the inspiration that goes behind that. We've sent tons of missions to the moon robotically for the last 2 decades, and you don't see that level of inspiration that you see with Artemis now. And, I was born a little after the last Apollo mission, but for people that are 10, 15 years older than me, I hear and I've seen, how inspirational it was to them. And those missions inspired a whole generation of scientists and engineers. And even if they didn't end up going to the space industry, that was the moment that they decided they wanted to be a scientist or they wanted to be an engineer. And my greatest hope is that Artemis can do that for a new generation of scientists and engineers. NASA has this thing called the Moon to Mars architecture, which is this big plan to go to the moon and then eventually send humans to Mars as well. And there's 3 key pillars there. One is national posture, which gets to the geopolitics you're talking about.
Yes.
One is science, and the other is inspiration. And we're going to be doing amazing science, but I think we've already knocked the inspiration part out of the park.
The next question is looking at public versus private. And we talked, and many know that government-sponsored teams and their state funding or their national funding, and you counter that with public. There's a public and a private competition that's going on, and you think of things like Starlink and so on. Can you talk a little bit about, I know there's absolutely an interest of human adaptation on the moon, as well as, and that's parallel to discovery and finding out as much as you can. Can you talk a little bit about drones and some of the other technologies that we can use that also can help with exploration that would not be human-centered?
Sure.
And who's funding it?
Yeah.
Who's driving that?
So there is a public-private partnership for a lot of NASA work. You mentioned SpaceX. That's one of the major, really big companies that's doing this. Jeff Bezos owns Blue Origin, which is another major company that is providing a potential human landing system for Artemis along with SpaceX. They have their hands on lots of other little, things as well. You mentioned drones. Starlink is a major SpaceX product. In terms of NASA exploration and the work that NASA's doing, they are contracted to do kind of specific things. Both those companies are providing launch services as well as platforms to land humans to the surface. They of course have other businesses. Some of those are paid for by NASA. Others they're doing on their own because they're for-profit companies. I'll also mention that there are lots of other smaller companies. And so, one of the ideas about going back to the moon is we can develop a cislunar economy, basically expand you have the big companies that are doing a lot, but if they can make access to the moon easier, along with some other smaller companies, then it's kind of like a rising tide lifts all boats type of thing. So NASA has a program called CLPS, the Commercial Lunar Payload Services Program, that smaller companies are providing essentially ferry services for scientific instruments to the moon. And so these are small companies based out of Pittsburgh and Houston and other places that are essentially roboticists and engineers. But it's not just about the big ones. Some of these smaller companies are actually doing a lot of work in helping us make access to the lunar surface easier. It's not trivial at all to land something on the moon. Yeah. So these companies are putting in some of their own capital and their own investments into into getting to the surface and developing their systems. So their investors are taking a risk, and their main contracts are with NASA. So the public has skin in the game as well in terms of our taxpayer dollars that are going towards that.
And Tim, to follow up with on the financial front on this, you mentioned earlier that federal investment had dropped from about 5% to just about 0.5%. What's your sense of the overall American appetite for spending money on space exploration?
I think it's variable, just like anything else. I feel like if you have 60% support, in this country, that's, basically a landslide. But, like I mentioned earlier, NASA is one of the agencies that has almost universal bipartisan support. Among the public, you often get questions about the value, which I understand. But you look at the educational opportunities, the technology development opportunities. We have more computing power on our cell phones than the Apollo astronauts did on the entire, Apollo spacecraft, right? And those were developments that were a direct result of our investments in space exploration. So whether it's remote sensing technology, weather satellites, there's all kinds of spin-offs that for technology that benefit us, every day. But again, beyond that, even people just think space is cool, right? Right. You see pictures from the Hubble Space Telescope or the James Webb Space Telescope. You see pictures from the surface of Mars taken by rovers. You have questions being asked about the very nature of life in the solar system and the universe with new measurements that are being made by Mars rovers. It's easy to get excited about that stuff. And I think it pierces this kind of public cynicism, that, we all kind of tend to have about everything. And so I think that's really special.
And speaking of technology and speaking of kind of human-centered curiosity and really wanting to make meaning in scientific discovery, there's always kind of this tension between humans and AI. Mm-hmm. And there's so much of that is part of NASA's success. Yep. And so I wonder if there's a couple highlights you can bring out that NASA has done very well in really showing how this technology, these incredible artificial intelligence systems that are using these algorithms for these really complex decision-making, coupled with human decision-making and innovation and creativity. Can you talk a little bit about how NASA's doing that well?
Sure. The best example, I think, is driving rovers on Mars.
Yes.
And so depending on where Mars is relative to Earth in the solar system, it's between like 8 and 15 minutes one-way light time, right? So we typically, when we have humans operating the rovers on the surface of Mars, we plan for a whole day's activities, send up that plan, the rover executes it, and then we get the data back, and then we plan the next day or the next few days as we've gotten better at this. But driving is something that we always had to be like, okay, we got to get to the next place. And as we've kind of expanded the distance that we expect the rovers to go, we can't just do this kind of every day. We have to let the rovers make their own decisions. And so very early on, I was involved with the Mars exploration rover missions in like 2004 to 2006 when I was a graduate student. And this was the thing. We would take pictures and, there's a rock there. We can't drive over there. So we'll kind of go around it and direct the rover to how to do that. But then as we started wanting to drive longer and longer distances to get to the next objective, some of the very earliest kind of AI, capabilities were in letting the rover decide what's safe and what's dangerous as it goes off, on its own and drives its own. And then we kind of wake up the next morning like, where did we end up? And those capabilities have gotten better and better. And Curiosity has been on the surface of Mars roving, sometimes autonomously, for more than 10 years. We're going to hopefully be sending a rover to the moon, a very capable rover called Endurance that's going to go thousands of kilometers over the moon, mostly driving autonomously. And so this is kind of a direct descendant of those early self-driving rover operations and AI systems. So even though we can have these rovers drive themselves, we still need humans in the loop to analyze the landing site, to figure out what rocks we want to sample, where we're going to take the next set of pictures and do our scientific analyses. So it's not like AI is doing everything and the rover is doing everything by itself to do our science for us. Humans are still very much needed. And this gets to the question of astronauts, versus robots. Even the thinking capabilities of astronauts to think on the fly, to make decisions that might not that might be outside of the initial plan. Those are uniquely human capabilities right now. AI is certainly making advances, but I'd rather have a crew member who's highly trained geologist on the surface of the moon than a robot that has been trained on some data set that I'm not sure exactly what went into it, right?
Well, Tim, we just wanted to thank you so much for sharing your expertise and insights today. We hope you'll come back actually and let us know how things progress with your work. We want to get the scoop. So.
Well, maybe you come back in a few years. I can bring an Artemis sample with me.
Oh my!
Wow.
All right.
Wow.
But this is talking about next level now.
Kidding,
So
right?
really appreciate it, Tim.
Oh, no
Thank you.
kidding. We hope our listeners find these discussions informative and empowering as Rick and I do. Thank you again for Tim coming on and your incredible, valuable contributions to Stony Brook, to science, but our understanding of who we are in this incredible, beautiful universe.
Thank you so much.
So for now, I'm Rick Gatto.
And I'm Judy Brown Clark, and thank you for tuning in.